guess we'll start.
Very small class today.
Yeah, I knew like 2 people were gonna be out.
Yeah, I talked to Kai, he told me to inform him about what he missed. I think he's gonna be here for lab.
Okay. Yeah, there's 1 straggler, which is good. All right, so let's at least start with some announcements. So just taking a look at the syllabus, let's orient ourselves. So we're, what, like almost halfway through at this point, or right at the halfway point? Just past. So we'll do our chapter 8 today, and then for lab, so I have both labs for this week printed out. So lab 8 is today, which should be really fun, kind of cartoony, modeling the tides. We'll see if we get to chapter 9, which is more what that lab is paired with today. So that's the goal, is to like touch on chapter 9, but we'll see. And then we also have prep, so looking at our lecture or syllabus here. So our dissection is coming up this week, so we're kind of going to skip around in our labs. And so that's to accommodate our field trip, so we have to wait on lab. So lab 9 is officially the plankton one, but we need samples to look at, so we're going to save that one for the end. So I printed out your dogfish dissection. So excuse the top page, I just X'd it out to try to help y'all so that you realize that this is from the previous lab. So your lab 10 just starts on the inside cover. So that might be good too. You're prepped for Thursday. So you probably want to read over that. And so I think we mentioned the alternative assignment, but I'll officially say it here. So again, Thursday.
Are we doing lab 9 at a different time?
Yes. Yeah, so I can pull back up this syllabus. So remember, lab 9, we had to push that back. And then note the date of the field trip, right, August 19th. So not this weekend. Next weekend, I'll be seeing y'all on Crescent City, if you can make it. Otherwise, right, you've already made arrangements with yourselves and your friends to go hang out on your own and observe. So dogfish dissection. And so if anyone is absent, so we do have, again, I understand situations come up. So if you can't make it or need an alternate assignment, it'll just be a 2-page, and that's just like front and back. So probably a single space, just paper on the dogfish shark.
I have a question. Does that include citations?
So then citations would be an additional page, right? So this page limit is just for the words. Fairly short though. All right, so that's for Thursday. And so also looking back at the syllabus, so we're again orienting ourselves. We have an exam coming up. Woo! And so we'll talk about today, again, what you might see, what you need to memorize, and then what I will provide on the exam. And so that's going to be chapter 6 through 10. So that's going to be last week and this week's material. So we're going to go through chapter 8, 9, and 10 this week. And again, I'll try to keep it light and broad like I did before, so people aren't stressed out over memorizing everything. So next Thursday, oops. Let me get the date back up for you. So that's the 17th. Exam, so just looking. And so right, August 19th. Field trip. And we'll meet 8 a.m. And we'll talk about that more as we approach, but just have that on your radar. Yep.
Since I'm doing the paper, do I have to come to lab next Thursday?
No. Yeah, and again, if you have to miss class 2 this week, then you can just do the paper assignment for the dissection, so we don't have to worry about trying to make that up as well. And let's see, other reminders. So our last organism journal is due this week. Woo! So, yeah, so that's out of the way. And, you know, if you're late on that, that's fine. You know, just try to get it in probably by next week would be a good goal. And that gives me plenty of time to grade, so just kind of looking towards the end. So that's kind of nice. No more organism journal. We'll have this ready for, so the idea is we have it for our field trip, and you can reference that along with your little sediment cheat sheet. All right, so we're almost done, and notice right after our field trip, that's our last lab, so we won't have lab anymore. I know, so it kind of lessens the load as we finish up, so this gives you time, right, to wrap up anything that you've missed. Good time to make up labs.
It's gonna start feeling like summer.
Yeah, you get a little bit of summer at the end. So right, we're kind of seeing the light at the end of the tunnel with our course. So hopefully feeling a little better, yeah. Get a few last rays of summer in there. All right, so let's dive in to chapter 8. And again, we'll take questions. And so now we're looking at the waves and the water. And so this is kind of repetitive, right? We're kind of just building upon everything. And so we mentioned before, most waves are wind-driven. And then a lot of waves can be generated by storms. And of course, these waves, right, transmit energy across the ocean surface. And then we'll look at, right, deep water waves versus kind of where people like to surf and those different characteristics. And then, of course, we'll look at tsunamis, kind of the famous and devastating long waves. Trying to make sure everybody. And so a disturbing force has to cause a wave to form. So, right, just imagine even just your drink of coffee or water, right, it's sitting open, or you could blow on it or maybe drop like a pebble in there. So you've seen that with a pond, right, how that will cause waves and ripples to go out. So that's on a small scale. And so now we can think about the ocean surface. So the wind starts blowing and starts adding energy. And of course, we have also the interface of different fluids of different densities. And so when you have, for example, air-ocean interface, right, you get your ocean waves. Air-air gives us more atmospheric waves. And then versus water-water interface, so that's going to be deep internal waves. So this is, right, more like just at the surface. This is going to be air-ocean, again, at the surface interaction. Above the pycnocline layer too. And then of course, again, our water is going to be your deep one. So just, right, we're looking, and we've talked about this before, right? That's again, the difficulty in modeling and understanding is you have your surface currents and interactions, and again, just the wind. So we looked at the wind currents. Now we're looking at wind water, and then we've mentioned, of course, right, the deep waves and the deep structures. So again, everything's kind of building on each other. And so first we'll look at these internal waves. And so again, this is going to be your top layer, so your pycnocline layer. So we have our surface and then internal, so right there in the boundary between the different densities and the pycnocline. And so these internal waves are going to be larger than the surface waves. So again, surface waves are more wind and shallow, so then our deep waves are down below. And so these internal waves can be caused by tides, turbidity currents, winds, again, if they build up deep enough, so with enough energy. And then so even ships, right, can create waves. It's called, what's it called when the ship passes? Yeah, the wake. So the wake leaves behind waves. So all that can create your internal waves. And of course, these internal waves, since they're a little bit deeper, right, so they're, again, right in that pycnocline boundary layer. And so we mentioned, right, submarines really don't go that deep, so this could be a potential hazard for submarines, these internal waves, so they can kind of push submarines off course or into potentially deeper waters that they weren't prepared for. And so let's look at the different types of waves and just what is a wave. So waves just transmit energy. And so we'll look at the cyclic motion of particles in the ocean. And so this is just comparing the amount of energy produced with these different forces. So we'll kind of dive into all these forces. But we can have our wind-generated waves. And so notice this is a wave period, which we'll talk about. So this is how much time it takes. But these are small waves. And then notice, right, the periods kind of get larger as we go on this scale. And so other causes of these kind of larger waves with more hour periods, and we'll again discuss this, could be tsunamis, and we'll go into details of thinking about much larger forces of energy and how those waves are different, how much larger those waves are. And that could also be volcanoes or large landslides. And then we also have ultimately, right, our ocean tides, which are essentially wave periods that are dictated by the moon and the sun. Well, this is, we'll get into with chapter 9. So that's kind of where we are. And so we also have to think about, and we just start with our ocean tides, that's kind of our main principal wave, right? But then we have all these other little waves being generated. And so as usual, the picture is very complex. All right, so let's look at the different types of waves. And so we have what's called a progressive wave. And so they oscillate uniformly and progress without breaking. And so there's three main types. And you'll probably want to know the difference between them. So that would probably be fair game on an exam. Again, I haven't written your exam, taking input, so you can tell me.
Are you basing it mostly off of what you're talking about?
Yeah, I try to, yeah.
Okay, because like, we, when I read the chapters, there's a lot of stuff that you don't necessarily go over in more depth, so I'm just curious if we focus more on the notes that you post.
Yeah, I
Would that be safe?
try to focus on like, yeah, the big picture notes, and then also like kind of the vocab terms, like big terms. And then I'll point out where there'll be like some math on the exam, but it'll be where I like give you a formula and you just have to like plug it in, so. Yeah, but I try to make sure that if I test on it, I at least talked about it somewhat in class. Like I don't like picking out random details from the text.
I appreciate that.
Yeah.
I appreciate that too.
But of course, you should read the text, right? Try to get that deeper understanding, but what I'm trying to test at is more a
Oh, yeah, of
surface.
course. I've just had several teachers where they will be like, all right, we're gonna talk about through chapter 13, but 14 and 15, you're gonna read the book by yourself and we're gonna test you on that.
Yeah.
And that's like hard because I can't ask the instructor questions while I'm reading it, so I was just curious.
And I've tried to read, but you got 4 chapters in 2 weeks, that's a lot of reading.
Yeah, it's a lot of reading. You know, just try to try to get through it, and that, that's the problem with the summer courses, but that's why I try to keep it, broad ideas that we've talked about so you feel comfortable on the exam. I want people to feel comfortable. I'll try to keep it the same level as I did the first exam, just like, big ideas. And we'll keep talking about these big ideas because they'll keep kind of coming up. And so let's look at these waves. So we have longitudinal waves. And so one would be like hand clapping, so you can hear that. A better example, which I thought about bringing in my son's slinky, but I didn't want to steal it from him. But a slinky, right? Yeah, so right, the longitudinal wave, where it's kind of compressional, and you can hold both ends and kind of slinking it, and you'll see that wave go back and forth. So that's longitudinal, again, back and forth movement. So you'd want to know that. That's probably a good broad ideas. And then a transverse wave is probably one you're familiar with. You've probably done this in like school at some point, where you take a rope and you can try to make a standing wave, And so that would be a transverse wave with our rope. And so what we find is that the ocean is actually a combination of these two movements, and so we'll note that. So orbital wave is basically a combo of our longitudinal movement and our transverse. And so the orbital wave kind of goes around in this little circle, and I was hoping the duck picture, oh, here it is, that's what I was looking for. This little duck picture. And so this little duck kind of shows you that orbital wave movement, where it kind of goes back and up around, right? And you've kind of been bobbing on the ocean, just kind of that circular motion. So it's a combination, again, of that back and forth compressional, and then also the up and down of the transverse.
Question.
Yeah.
Think you're in a bathtub and you're a kid and you're like going to slide down the bathtub, if you will, and letting the wave bring you back with one of those, that technically fall under.
So it should kind of give you the orbital wave motion. It kind of depends. And so you played with that right in the other lab, because if you kind of get it more flapping in probably like a smaller setting, that gives you more of a transverse standing wave. Yeah. All right, so back to this. So again, we have our orbital wave. And so that also, these waves transmit energy along the interface. And of course, right, we have our air-water boundary right here as well. And this also helps us transmit energy between different densities. So we'll see that motion. All right, so this is just the text that corresponds to what we said. So again, recap, right, our longitudinal, our compress and decompress waves, again, the back and forth motion, like a coiled spring. And then we set our transverse, or our side-to-side waves, go like that, kind of following, right, our sine, a sine wave, right, that goes up and down, up and down. And so it's generally only transmits through solids, not liquids.
What does that mean?
So liquids are going to be more like your orbital waves, or like sound, right? So you can hit the desk and that'll transmit the wave through it, whereas a liquid.
Solids are making these waves now.
No, it just means like the medium, right? So again, you hit the desk, and so you can feel, right? You feel that energy. So you can feel it, right? Nothing's moving, but it's just that energy is being transmitted.
But wasn't that the kind of wave we saw when we were doing the lab?
No, that would be the.
Well, if you can get it, yeah, the transverse waves, because we were getting,
Isn't that the kind we saw in that little example?
yeah, but it's also like a small container, right? So you're kind of limiting the movement, essentially, right? Because it's not like the ocean where you're getting like the whole currents and the tides. So this is also like light waves. Oh, well, light would not be solid, so I'm saying light is another form of a transverse wave. So, let's see, I'm trying to figure out what,
So we're learning about transverse waves even though they're not actually part of the ocean.
yes.
So where do these waves occur then?
Well, I gave one example of the solid, yeah. So vibration.
Okay, so these aren't actually waves in water.
No, because the waves in water, so I think, yeah, what's confusing is this should really be, right, like not the ocean. So that's all it's trying to say. Or again, right, your rope. So you can't really do that with the rope either. I mean, with the liquid, getting it in the transverse wave.
So these are basically just vehicles for the energy.
Right, yeah, so they,
So that's just-
energy,
So for these to work, you have to have something solid, something that you can actually, essentially hold or feel to move that energy along.
right, or there has to be something that initiates the wave. So maybe, backing up, maybe that makes more sense, right? Because there has to be something that originates a wave. So
like
yeah.
when you hit a baseball and you feel it at the end of, you hit the ball with the club and
That's-
it vibrates down to your hand. Would that be kind of what you're talking about?
Yeah, if you're talking about just the vibration,
Yeah, it would
so
just
that's,
be the
yeah,
movement from you hit the ball and then you feel it all the way down in your hands.
yeah. So does that make sense for people? So it's just like transmitting
It's
energy.
just a vehicle for the energy.
Yeah,
Like where the ropes leave the ground, basically.
yeah, so you're doing like, I mean, it doesn't really work with a jump rope since you're,
No,
but if
but
you,
when you're doing it like this.
yeah, if you're going up and down though, right, that would be, you have that energy, it's being transmitted along the rope. And so that's the other thing. So I guess the transverse wave, why they say, so I've not to get hung up on it. So all they're saying, right, is that with the transverse wave, there's no movement of the object, right? So the energy, like you said, is just traveling through the object. So the object is just staying there. And then what we see with the ocean is, again, the combination of those. Because you do see, right, the transverse wave effect, but then you also have it going out with the compressions, right? And so that's why we say that the ocean has the orbital wave. So, right, yes to ocean.
So does the ocean not have the longitudinal?
So it has the
It just
combination.
has both,
Right,
not
right.
one.
So what you see in the ocean is the effect of both of those waves, because it's not just a purely transverse wave, and it's not purely a longitudinal. There's both compression and up and down, which is where you get the orbital. So that's the distinction that those notes were trying to make. So that's all this was trying to tell us, right? Is that we have our longitudinal waves. Those are, again, are back and forth. And then transverse is anything up and down side movement. But with the ocean, you get more of the orbital wave interactions.
I think the confusion's coming from the word wave being used, and obviously it's not incorrect, but at first I was thinking of waves,
In the ocean.
like the ocean waves, not like waves of energy, or waves of heat, or waves
Yeah,
of.
because we wouldn't be talking about ocean tides and tsunamis into this.
Well, right, but we have to talk about waves fundamentally. And so this is just a definition of a wave.
It just took us a long time to get to that, I think.
Okay, well,
We're
just
there.
keep hanging with me, because we gotta talk about a wave still. And so we can define a wave, and this is similar to how you would define any other wave. So just comparing it to a more simple transverse wave, which I drew horribly uneven. And so we can look at these different parts of it, and so you'd want to know this. So we have the part where it's the lowest, and so that's called the trough. And so, right, you can see that here. So it still applies with our orbital wave. Then we have the crest. So that's going to be the highest point. And so they have it labeled here as the still water level. So that's this line that I've drawn. But the better term for it is we want to identify these nodes. So nodes are going to be where you have no movement. So again, thinking of just your rope, and you can get a standing wave, so that node would be at the still water level, but it's not moving, right? Does that make sense?
So is that the baseline of where the waves would start? So if the waves would stop, that's where it would all go back to?
Yeah, so yeah, if the water was still, it'd be the same level as the node. And so with that, we can also define, so the crest and the trough can also be called antinodes. And so antinodes just implies, right, either the highest or lowest part. So this is an antinode. This is an antinode. And so there are a couple of characteristics that we'd want to measure. Let me.
There's the map.
Yeah. So we have our wave height. And so let's look at our wave height. So this is going to be defined as all the way, let me switch colors, from trough to crest. So this is height, and you can see that labeled here, wave height. And then we have our wavelength. And so our wavelength, notice, is either going to be crest to crest, so highest point to highest point, or if you measured from trough to trough, that would also give you the wavelength. There's our wavelength. And so there was this important calculation that they mentioned. So they have our wave steepness then can be defined as our wave height over our wavelength. And I think, again, I'm not sure if it will pop up on the exam, but this would be fair game because it was mentioned many times in the text, so I think that this is fair. And so it mentions if this ratio goes over 1/7, then your wave breaks. And so then wave period is the time for one wavelength to pass a fixed point. So you guys kind of did that, right? So you had to see when the waves hit a fixed point, the end of your little bath. And then your wave frequency is just defined as 1/T. And then so our diameter of orbital motion decreases with water depth. And so the limiting factor is the wavelength. So wave base is 1/2 of the length. And again, I'm not going to make you memorize these formulas. I'd probably give them to you. So I'll just start this as, again, you should memorize this. But other things I will give to you. But you would just have to know like what L is And it could just be like labeled on a diagram, something like that, or in a word problem. And so again, here's just another diagram that shows it maybe a little clearer. Again, your wavelength, right? So crest to crest. Again, we have our still water level, and that would be the node. And then half wavelength corresponds to our wave base.
I'm a little confused with the verbiage of still water, because is that, it looks like the water's still moving, but is it?
That's if the water wasn't moving at all, that's where it would level out.
Yeah.
Okay. That makes sense.
Oops. And so again, our circular orbital motion is what the ocean waves are. So again, our combination of our transverse and longitudinal waves. And so that gives us this little circle where you just kind of bob around and don't really move. And of course, right, the energy, though, keeps advancing forward until, as we see, right, it hits the shore or something. Okay, feeling okay so far with waves?
I was just thinking, as it comes up, rises up and comes towards shore, and you can see it going that way, is that because of the orbital motion of it?
Well, that, and so you're kind of skipping ahead, but we'll look at exactly what causes those different waves. So we'll look at, right, the different types of waves, but it's basically with how steep it is causes a different shape. But yeah, you're right, right? So it still has kind of that circular motion, and then how it breaks depends on the seafloor, but so that's later on in our chapter. And so in general, right, our deep water waves, so it tends to be less since our orbital motion, again, tends to be limited by that. And again, we know we can have deep waves, but because of this, they can still put out large structures out here as long as, right, they have a large mass, especially below where those deep waters are. And so here's an example of an airplane runway, I'm sure used for some military base. What else do they, oh, like ocean drilling. So again, their mass would need to be below the typical deep water waves so it can withstand the waves and not get caught up.
You're saying the runway has to be deep enough?
Yeah, so there's like some sort of deep structure right below, and it has to go deeper than the deep water. So deeper than, right, our typical orbital motion. So going back, right, to this formula. And so we'll kind of look and see, right, so waves have been kind of characterized. You kind of know typically what height the wave is going to be in certain parts of the ocean. And so, right, they calculate roughly how deep then their base has to go. So there has to be, like, ideally your center of gravity would be down below there.
So that green line?
Yeah, so it'd be below that green line. So then when the wave comes, your whole base is stationary and not as affected, or, right, the oil rig, whatever you're setting out there. So that's how they engineer kind of around that issue. And so again, we have our wind-generated waves in open ocean. And so this is kind of a typical speed calculation. So just wavelength over your period in time. But again, I think I will provide this formula for you. So you would maybe have handy formulas either at the beginning of your exam or dispersed. And then they have this special speed for it, since this is, again, the speed of really the energy, right? Because the water's not flowing by at this speed, just the energy, the wave is moving. And so they just have a special unit called celerity with this C. And so The only thing you might want to be aware of is, you know, if I just gave you a formula kind of like this, do you know what it means? So that's what I would be prepared for. So like be able to understand, oh yeah, that's supposed to be length, that's supposed to be period, especially if you read it right in the context of a problem. Yeah, it's gonna be your period. So yeah, so like at a certain point, how many?
By speed, is that like wind speed, the speed of the wave itself?
Yeah, so the speed of the wave, right? So the speed of the energy being transferred.
It's kind of amazing that the water molecules really aren't moving forward, they're just going in circles, but it looks, when you see the waves, it looks like the whole thing is moving.
Yeah, it's really more just, yeah, you're up, down, and how tides are. And so now this is just a graph correlating speed roughly with our wavelength of these deep water waves. And so you can just see, right, if you have a period of 8 seconds here, then that corresponds to 12.5 meters per second. So with a wavelength of 10. And so now looking at shallow wave waters, so this is defined as when water depth is less than 1/20th of the length, right, of our wave. So now the water, and this is starting to get into, you know, waves and surfing, but now the water, right, feels the seafloor, so that kind of pushes the energy up as well, so that can cause different effects. And so let's see, so then we have our speed then changes. So we have a different formula, so now this is all this is saying. So review, right, this is for our big waves in our open ocean. But now if we want to correlate it to our depth, we have this different formula where we have, again, our celerity, and this is in meters per second, is 3.31 times the square root of the depth in meters, or again, this is the formula in feet per second. So again, given by the depth.
What does that mean, less than one?
So this is just where the ratio, right? So if it's 1/20th the length, so this would have to be the length of your wave, right? So then anytime that ratio that your water depth is less than 1/20 times the length, right? So you just take, let's just say, so example, all right, the length of your wave is 100 meters. So then 100 divided by 20 gives you 5 meters. So anytime that the water then is less than 5 meters, you would get these shallow water waves. That's all that's saying.
I have a feeling you think we're a lot, some of us are a lot smarter than that.
No, I mean, I think you don't give yourself enough credit. It's literally L. What is L? Define the variable, right? We were just talking about length. So length of the wavelength, and then you just multiply it. So, you can plug in any number. That's all we're saying. So it's just a relationship, because we don't know where the shallow water wave is going to occur unless we have the wavelength, right? Does that make sense? And then all it's saying is when you have these conditions, so again with our little example here, so we said, okay, we're in these shallow water conditions. Let's just say we're right at the limit. We'll say we're at 4 meters. So that's going to be our depth. right? So now it's telling us depth is the seafloor. So now we can say, well, now we can calculate our expected speed in these conditions. So being consistent with these meter units that I picked, all we can do is plug it into this formula, right? Plug in stuff in. Let me find my calculator, sorry. So second square root of our depth. So again, this is just a dummy value of 4. This would be provided or indicated times 3.13. And so that tells us our expected speed then of these shallow water waves in our dummy conditions would be 6.26, and that would be our units of meters per second. Does that make sense? And so I would expect to see something like this on the exam. Again, I'm not going to make you memorize all these formulas, but I would make some sort of word problem scenario, calculate, are we on shallow water conditions, maybe verify that, based off of the length, and then, calculate the speed then, and I would give you these formulas. So I'm not expecting you to memorize the formulas, just plug in the values. This is a formula of 3.13 times the depth then of your shallow waters.
So what would be considered shallow?
Well, that's what we're saying is it's dependent upon the length of the wave that's coming in, whether that creates those shallow water conditions or not.
So it would be considered shallow water if the depth is less than 1/20 of the water.
Exactly, yeah.
So when we're doing meters, we're always doing 3.13? I don't understand.
Yes,
Okay.
yes. So if it's in meters, it's always this formula.
Okay.
And if it's in feet, it will be in that one, or whatever the conversion, right? It just gives you kind of easily accessible formulas. What don't you understand?
I'm not good at this kind of math.
There's like almost no math. It's literally multiplication. You got to stop.
You, it's no.
No, you're putting a mental barrier to yourself, and you need to just relax, right? So step 1, it's saying, well, let's define the conditions, right? Now, hang with me. So what's the issue? The condition is defined as when your water depth is less than 1/20th of the length. Okay, let's do a new scenario. Let's say our wave, and I don't even know this is reasonable, but let's just say our wavelength then, so L is 500 meters, right? So now we need to establish, well, under what conditions will we have shallow water waves? So then we can turn to this formula. Okay, once it hits 1/20th of that, now it's going to feel the length, right? Because remember, the length also dictates the depth. That's where this is all coming from. So now let's just plug this in, okay? 500 times 1/20, or divided by 20, right, all the same thing, 25. So now once our depth approaches 25 meters, now that's where we have the shallow water conditions. So then we say, okay, our shallow water waves will occur now at 25 meters depth, right? And this is going to be depth of your seafloor. That's what this is referring to. So now this is D. And so now anytime you are less than that, so 25 or less, now you can invoke these equations, right, and say, well, now we can calculate the speed of that shallow water wave coming in by just plugging in the depth there.
So C is the speed again, right?
Yeah,
Even though in
C.
the book it has it as S?
Yeah, because this is that celerity, so this is, or speed. So yeah, don't let the units, them switching units confuse you. It's the same thing. They just use a C here because that's supposed to be wave speed as opposed to, right, velocity where you're moving speed.
So is the first step basically to categorize it, whether it's shallow or not, and the second step is to find the speed?
Exactly, yeah. So does that make sense, right? So first step, you're just saying, is it shallow or not, right? And then we're saying, okay, if it is, that's the speed of the wave coming in. And so, and why we need to recalculate it, so we can have, right, obviously we have wind-generated waves in a shallow nearshore area, and that's normal. But what gets scary is, right, those tsunami waves are a lot larger, and we're going to talk about them more. But it's the same thing, so what's scary, and you kind of mentioned this when you're talking about, right, it's like, it looks like it's moving forward, but it's not. So that's what's scary about the tsunami wave, is that trough, right, is so low, and then they get that weird, like, ultra low tide effect. And, you know, again, we'll talk about the monitoring, but if you see that low tide, like the really low tide, that's where you got to start running. But even then, I don't know if you'd run fast enough. But then you'd get, right, the opposing crest, the high tide, and that's the devastation of the tsunami. And of course, at that point, right, that's where it comes in super fast. And if it's super long, right, with a tsunami, a huge wave, that's, you know, that's where it's going to be fast and devastating. So that's why they say, right, you can't really outrun a tsunami wave either. All right.
They like to put those signs on the coast.
They
People
do.
run.
It's so funny.
Okay.
Like, I don't think you're going to outrun him, but anyway.
Feel an earthquake first, then you know to run.
And that, I mean, that is part of the warning systems, which we'll talk about, is like, yeah, they'll measure those, the earthquake waves first, since those travel faster through the earth, so you, right, your solid energy waves. And then, yeah, you take that, and that's where they issue those tsunami warnings of, oh crap, that means the water wave is coming.
Because we had that, or Japan had that, what, 10 or 12 years ago now, that big earthquake that messed with their nuclear.
Yeah,
sites. And then
Fukushima.
They were saying on the west coast we were going to have tsunamis, and they, obviously it didn't get as bad as
Yeah, I
they
do
said
remember.
it was going to be, but,
All right, so then these are just transitional waves. And so the main thing that we want to take away from the transitional wave is it's just kind of that in-between of deep water, shallow water. And so it's going to have characteristics of both. And again, your speed. So again, we're not quite thrilled that the book goes back and forth between S and P, but it's fine, whatever.
I don't understand why that one's called transitional. It still looks like orbital.
No, transitional. Now it's just saying that it's like both of them. And right, because it's intermediate between our deep water and shallow water. So it's different.
So this is just depth, not the wave type.
Yeah, it's based more on the depth.
They should not have titled it transitional wave. Right?
Yeah, it's kind of confusing. So let's see. It's okay. All right, so let's look at wind-generated wave development. Oops. And so it starts off as little capillary waves. So you have, right, just little like ripples, kind of, again, if you blow on your drink, you see little ripples. And they have little V-shaped troughs. And so look at how tiny these wavelengths we're talking about, right? So wavelengths less than 1.74 centimeters, so pretty small. And I like this little graph because it kind of shows us the action here. And so, right, if these little capillary waves keep picking up wind energy, they're going to eventually start growing. And so then they get into larger kind of gravity waves and more energy. So this is now just developing gravity waves as it picks up energy from the wind, and more energy is just transferred. And then again, eventually, if we get a wave breaking, this is when our wave height exceeds this 1/7 ratio. So, yeah, the small ones are capillary waves. And then it just builds into gravity waves. And so, right, again, your capillary waves would be ripples, you know, again, little ripples in the pond, or just the initial stresses, right? So especially if a wind just blows across a still pond or lake, you see those little ripples. But if the wind were to keep blowing, and keep transferring energy, then you get those waves. And again, so we mentioned this 1/7 again, so I would expect 1/7 to come up. So this would be, again, when your height exceeds this 1/7 ratio. All right, we could do an example. So if our length is 70 meters, and then once it exceeds, so once our height gets to even, let's just say, you know, 15, then, right, it would get a crash. So that could be something that I give as, like, you know, based off of these ratios of heights and length, which one would have a wave break. So again, anytime it exceeds that ratio, so if you did, right, 15/70, that's 1.5/7, so that's greater than 1/7. You can always convert 1/7 to a decimal if that helps you, right? So then you're just looking for something greater than that ratio. Oh, sorry. Ready? And so this is just defined as where a lot of these wind-driven waves are generated, so the sea area. And so, again, that's just really broadly defined, probably just thinking more of like the Pacific Ocean, where you have your big area, you're going to have a lot of winds moving. And so, of course, all the factors that affect wave energy. So we've kind of been dancing around this, but here it is. So, right, of course, the wind speed is going to have an effect on how much energy is being transferred. The duration, so right, how long that wind is just going in that same direction, building up energy. And then the fetch, and this is a term that you might want to know. I don't know if we'll test over it, but it does crop up in your book a lot. So this is just the distance over which the wind blows. So how far does that wind reach? So all of that influences the wave energy. And so let's kind of look at the little diagram, right? So this would be out at sea where there's essentially no land. And so it's just building up of, again, our air movement. So if we have a storm coming and the wind is going to be blowing in a certain direction, and so notice, right, the fetch, so that's just where the wind is blowing. And so, of course, right, greater fetch, more energy. And then we see the direction that the wave is going to advance in. That's going to give us swells, but we'll look at that. And so we mentioned that these wave heights are directly related to our wave energy. And so again, this is just kind of typical statistics. So wave heights are usually less than 2 meters. And breakers called white caps form when waves reach their critical steepness. So again, referring back to that 1/7 ratio. And then we have our Beaufort wind scale that just describes the sea surface and then also correlation. And so this is just satellite imagery now, looking at our winds, our wave height. And so what do you kind of notice? What jumps out at you, and what can we say, maybe, and relating it back to the other chapters?
Southern hemisphere has some really big waves.
Yeah, and what do we remember about the southern hemisphere? Like, whoa. Yeah, so it was super windy. And so, right, and I think in our previous chapters, there was, what, like the roaring 50s or something? I probably have it wrong. I think it was in this book again. Oh, there we go. Yeah, the roaring 40s, the furious 50s, right? So this is all relating back. So this is kind of cool, right? So we studied before that all the wind travels here super fast. And so all those windy conditions, right, they also created those fast-moving currents. We mentioned that, how right around this cape here, that's super fast conditions with the currents. And then we're also seeing that reflected in the wave height. So it's kind of cool, right? Everything's just building and re-emphasizing everything. Oh, the Screaming 60s, I'm just rewriting it. It's not that important, but it's just to help you remember, right? Winds moving super fast in the southern hemisphere, and all that leads to really big waves and really bad sailing conditions. So we've kind of talked about that, how this area's been a little dangerous to sail historically, and I'm sure still is to this day. And so we can all see that with the winds. And so then we just have this nice little scale, and we can just appreciate it, and just appreciate how it goes from 0 to 12, where 12 gets us all the way up to hurricane wind speeds. And then comparing that to back at 1, if you had a completely calm day, right, your sea should look like a mirror kind of reflecting at you. And then just notice, right, light air with little ripples, that would be a 1. And you can, again, kind of read this for yourself. So strong breezes are defined as a 6, where you get large waves, and that's where you see some white caps everywhere. And then now we get to gales, which get more dangerous, and start getting more like storms or big rolling of the seas. So this gets, right, obviously scarier conditions and violent storms. So then we can get into really large waves. And so then there were some theories about the maximum wave height for a while. So initially they thought, well, that was the ship, right? And then so the ship was 500 feet long. Yeah. But then, Well, the convenient thing, right, is it was able to use kind of the ship, its measurements to kind of measure the wave height. So this was pretty fascinating. So again, at the time, they thought they couldn't go above 60 feet, but they observed some 112 feet high. And I think very luckily for this ship, the Romana Po, it was riding with the waves, so even though it was pretty violent, these waves, it still managed to survive being tossed around. So that,
Yeah, so those big ships, so I was in the Navy, my sisters are in the Navy, so they don't, you never wanna go like this. You know, I forget that's pitch.
oh,
So it's terrifying to watch. I've never been on a ship, but my sisters saying they go up on the crest, and then they dive into it, and almost half the ship goes underwater, and it pops back out.
yeah, that's
Yeah.
terrifying.
And you're
But-
talking, I mean, aircraft carriers do this.
No,
Like,
thank you.
ones with like 4,000 people on it.
Oh, gosh.
Yeah, no, the ocean terrifies me.
Yeah, I agree with you on that.
When you can just throw you know, something, a small city around like that, nope, I'm good.
Yeah,
I'm going on my first cruise next month.
well,
You
What-
probably won't go into the deep water with
Yeah.
it.
cruises keep you safe, though.
We're going north.
Oh, yeah, so you'll take, the nice current up there and it'll be safe. But, my husband and I were just talking about this, like, that's why cruises just don't go out in the Pacific Ocean and park out there. You could get tossed.
It's scary what what they say, like the fleet side has to deal with, like, I can't imagine, because during, if something all of a sudden happens, you have people on top of the deck, like bad,
Yeah.
planes down and stuff, and it's like, no thanks.
Yeah, that's
Wow.
terrifying.
Then they just lock the whole thing down, and then you're just a tin can.
Yeah, and so again with this ship, if it had been like what you were saying, if it was facing like the other way and not with the waves, so not riding up and down, yeah, it would just be,
Slapped back and forth, people would die.
yeah, you'd be obliterated.
That, they're using the momentum, and like the way, you never go against the grain, you go with it.
Yeah.
Even with small boats, like when I was taking my fishing boat out, you never wanna be in the middle of, if it's like this, you'll just get knocked around, you wanna go with the
Yeah.
flow. If you fight it, you're gonna lose.
So good pro tips, and this is why, I mean, I agree. If there's anything I learned from teaching this is I'm more scared of the ocean. No, it's like terrifying. It's huge. It's hard to imagine. And
Yeah,
so,
see?
yeah. So luckily and amazingly, right, this ship was
That's part of this
undamaged.
deck. That's metal.
Yeah, these are so big
She's
and
got
bent
these
to-
It went down and it came up, and the pressure of the water just bent that.
Yeah, so so you catch a wave wrong and you get bad destruction. So, and this was pretty terrifying in your book. It said that like 1 to 10 large ships disappear every year and like hundreds of small ships. That was kind of scary. I didn't realize we lost that many container ships still. I mean, amazing how big the ocean is. So wave energy, so of course at sea, right, with no other land, you can get out to big oceans. And then eventually if you approach equilibrium conditions and your waves grow no further. And then when we have swell, this is uniform symmetrical waves that travel outward from a storm area. So you might be able to use a swell to kind of predict some storms, forecasting. And then these swells, since they're kind of being elongated, so swell kind of referring to swollen in a way. So, right, they kind of get swollen and get longer crests. So just peeking down, so all this table is showing us is, again, we can just like appreciate what it's telling us. And so, right, we have wind speed, the fetch, so again, how far that wind is traveling, and then duration, so we mentioned, right, how long also influences. And again, this is just an average, right? So just take this as a rough guide, and we're just, again, appreciating it, so we don't need to extract anything. But you can just see, so wave height, right, starts to increase. Obviously, as we get more wind speed, greater fetch, and greater duration, that makes sense. Average wavelength also goes up, so just kind of note that, right, both of them increase, so height increases, wavelength increases as we get to greater and greater energy. And we can just think of this as energy increasing broadly, right? So wind speed, fetch, duration, all that really is energy. And then your average period, so you go from little small waves to much larger waves. The longer period, so longer time to come, but also a lot bigger. And then this is just the highest 10% of the waves with those conditions. So trying to give you an idea what more extreme waves you might see. But of course, right, like we just saw, you can have really large waves. And so let's look at kind of swells. And so again, these longer wavelengths travel faster and outdistance our other waves. And so we can have what's called our wave train. And so let's look at all these characteristics. So if you have kind of your leading wave, so let's just say, right, even imagine you drop a pebble in, right, you have your first wave coming out. But then if we have like a storm or wind that's continuing to generate waves, so this is where we would see this. So you have your first wave, right, so that's your leading wave. And it's going in our circular orbital motion, right, across the ocean. And then eventually it'll die out. So we have what's called wave dispersion. And so this is just sorting waves by wavelengths, but then it also will disperse. And then decay distance is distance over which wave changes from choppy sea to uniform swell. And our wave train speed is half the speed of our individual waves. So these wave trains are just coming off right from like your main wave. So again, you're imagining a storm coming. We might have to go back to this picture for us. Where's the picture? Sorry. Oh, no, I can't find the picture. There we go. This is a picture I was looking for. So right, we have winds being generated, and again, these are our swells kind of advancing from our main wave, right? So this is our fetch. So we have our C here, and then these little waves are coming out from there, being generated. And so again, our wave train speed would just be half of the individual wave, but again, I would give this to you on an exam. From like our, so it's basically talking about choppy seas, so where the storm originated, so just thinking back, right? So you have your choppy sea, your storm, and then your swells are going to be coming out in front of that main storm, basically. And then, so with these swells, I'll try to zoom out so people can finish. But all we're appreciating is how this wave keeps going. So wave 1, right, it dies out, but now a new wave is generated. So wave 5 is behind, and then it keeps just traveling, and then, right, wave 2 dies out, but then you have new waves. So it just keeps kind of dying out, and new waves come behind it. And then again, it mentions that our group speed is 1/2 that of our individual wave. And so this is pretty important. this wave interference pattern. And so let's talk about this. And this also tells us maybe why the wave heights are a lot larger than we would expect. And so we have what's called constructive interference and destructive interference in wave patterns. And so basically, if you have two waves coming in and they're in phase, so this means, right, they're together, so their heights match and everything. So right, crest matches with this one's crest. And so basically, you can add them, right, trough with trough. And so the resulting is that you have a larger wave. So, right, it has to be waves of the same wavelength. They come together and then produce waves of a greater height. So that's what gives us, right, really large, unexpected rogue waves. So, right, this could be our cause of rogue waves. We'll find that a little later, but it's pretty much self-explanatory. And so again, I would note this, so we have constructive interference. So this is in-phase wave trains. So you want to know this, so this is important. And so we can also have what's called destructive interference, where we have out-of-phase wave patterns. So instead of matching up, now it's going to match up where the crest matches up with the trough. And so this gives you destructive interference. So essentially, the waves cancel. So it comes together, giving you some canceling effect. And of course, right, there's also a lot of mixed interference. So that would just be when you have waves of different lengths and different heights. And, right, the resulting pattern could be complex. So this also gives us, again, a lot of unpredictability. So you can see how this might work. So a large wave and then trying to mix with the smaller waves. And you can even think about this, right? This is why everything is so complex. So thinking back, we have our big tides from the moon and the sun, which we'll talk about in the next chapter, right? So we have our big tides. So our big waves, but then essentially, right, all our other little waves by everything. So it's anything from, you know, a rock, a landslide, volcano, eruption, you know, wind. So there's so many things. So it's super complex. And so, right, we would expect, of course, a lot of mixed interference in the ocean. So a lot of different swells of different wavelengths and different waves coming together. And so again, you can just appreciate how complex those wave patterns would be. And so we mentioned rogue waves. And so rogue waves are basically just massive waves that people aren't quite sure where they originated from or maybe not expected. And so all this means, right, and maybe they have some idea, but these rogue waves are probably where you get these really good constructive interference. So that's going to cause really high wave heights to come up. And of course, right, they have abnormal heights then if they're probably constructive interference, really high. And obviously with big heights, you have destructive power. And so apparently the luxury liner Michelangelo was damaged, so you can appreciate that. So really crushed and kind of terrifying. Anybody see The Perfect Storm? Yeah, I forgot. When did that movie come out? It's been a while. Yeah. I think they remade it or something. Poseidon was a new one, maybe? Question mark. Nice. So yeah, that's where they get good horror stories for big waves. Yeah, rogue waves. And of course, right, they're difficult to forecast. So again, we're seeing this, right? So if you have a lot of different potential places and ways to generate waves, obviously it can be difficult to forecast where you might have a large wave. But we might expect it to occur, of course, near like weather fronts or downwind of islands. So depending on those islands, reflect those waves. And so we can also have strong ocean currents that amplify opposing swells, so that could give you a rogue wave as well. And so they have, I like our poor ship sinking in this. And so looking, first of all, note where this example is. So down in the south, right, where we mentioned they have pretty fast currents. So we have our scenario, our strong ocean current, such as the Algujas, which I'm not sure if I pronounced that right. So it flows in the opposite direction of a large wave, such as those generated in the Antarctic waters. And so those hitting can then generate a rogue wave. And so, of course, it mentioned that it can damage even a large ship. So pretty scary. And we had our helpful tips of the day. You try to ride the wave if you can.
Don't go to the ocean.
That was not very cool. I was really looking forward to it.
Engineering was fun, go do it.
I'm sure the cruises are fun, they follow the coast normally.
Yeah, yeah.
They're not, you'll see land.
Yeah, you'll be safe. Yeah, just
Not
don't,
in the middle of the Pacific.
yeah.
Or the Gulf or anywhere really scary.
I think the Gulf is relatively safe. It's more the Pacific that's scary.
I don't trust any of it.
Okay, maybe like the Bermuda Triangle and the Atlantic, I wouldn't go there.
Well, there's so, I forget what the number is, but it's a very small percentage of what's been discovered in our ocean, like what's been explored. And that terrifies me too, because like what else is down there?
Yeah.
Like, I mean, for all we know, Godzilla is real. I mean, there's,
Yeah, I haven't heard about the Loch Ness Monster though recently, so I don't know about him, but yeah, I guess maybe Godzilla's hiding. Or, yeah, wasn't there a new like Jurassic Park movie or Megalodon Meg?
Meg.
Oh, it's
But
bad
even
movies.
the creatures we have found down there are all terrifying, like the lanternfish,
Yeah.
the anglerfish, and like everything looks like it wants to kill you.
Can't judge them by their appearance. They're just trying to survive in the dark. Poor little creatures.
By the time they see them, they're like, pinch us.
Yeah, like that kind of, like the size of the things in the ocean too, like, just the thought of like a whale being next to you, like, they're not gonna eat you, but they don't know how big they are compared to you, so they're just gonna run you over.
Yeah. Plus, isn't there like sharks haven't evolved in like a really long time
Yeah,
because they just
they're
hung out in the
like
ocean?
dinosaurs.
Yeah.
They haven't, there's no reason to, I guess they're just the perfect animal.
Hey, it's awesome. All right, so now let's talk about surfing, maybe. So you're kind of asking about this. And does anybody surf in here? Oh, nice. That's awesome.
Not up here, not in Oregon.
I don't know anything about surfing.
You have to go deeper and it's colder.
Uh,
I grew up in the Bay Area.
so yeah, our surf zone is where we have the zone of breaking waves near shore. And we have our shallowing water, where our water becomes gradually more shallow. And so when the deep water waves enter our shallowing water, then unless they're half their wavelength, they become transitional waves. So this is, I think, the part that was confusing. So now we can kind of track it. So so now we can say 1/2 L for depth. That's where you start getting those transitional conditions, right? So now just kind of putting everything back together. So we mentioned, right, we have the shallow water conditions were defined as 1/20th. And so now looking forward, okay, wave is approaching, so then we have transitional waves once the depth hits about 1/2 the wavelength, and that kind of matches what we were saying with the little orbital currents, that they only go so far deep, right? So they only go to about 1/2 the length, so that's why we say, well, once we start getting where the depth matches that, that's where we get the transitional wave. Then that'll switch towards, more shallow depth. And so as our deep water wave becomes a shallow water wave, our wave speed decreases, wavelength decreases, and wave height increases. Everything's decreasing except our height. And you can kind of see that, so you can imagine as your depth, your depth is decreasing. And so that almost kind of pushes up your water and giving you your surf zones. And so again, they mention our 1/7 ratio pops up again. So this is where, again, you're going to have your wave break when your steepness, again, exceeds this ratio of 1/7 the length. And then, so we mentioned breakers in a surf zone, so you were asking about that, is what kind of causes cool surfing patterns, and maybe all have good stories. But, so you surf as your swell from distant storms, so, usually that's why people like to surf right before a hurricane. I'm sure you've, yeah, so usually people try to get out there right before the hurricane hits, because they're riding those big swells from the approaching storms. So you always see a few brave souls out there. And of course, your wave breaks close to shore. And then we have our surf, of course, generated by any sort of local winds. And of course, if you're in a hurricane, that can give you choppy waters. And so there's 3 main types of breakers. So if you have a spilling breaker, this is going to be when you have a gently sloping seafloor, so your wave energy kind of gets expanded over a longer distance. And so this means that your water slides down the front of the slope of the wave. So you can kind of see that. So from what I understand, this is not as great for surfing. And then versus your plunging breakers. So now when you have a moderately steep seafloor, then your wave energy gets expended over a shorter distance. And so now you have these nice kind of big waves going, your plunging waves. So these are supposed to be best for board surfers. So you said you surfed off of the Bay Area. Where did you surf?
Same, done Santa Cruz and up in Marin County.
Nice. So I assume they have probably plunging breakers, waves.
Yeah, or, I mean, shoot, some of, even when you don't necessarily, just the nice big rolling waves are even kind of nice too, especially when you're learning. And they don't actually.
Didn't say where these pictures were from. And so then we also have what's called the surging breakers. So this is just your steepest now in comparison. So of course energy spread over the shortest distance. And so this one says it's best for body surfing. I've never gone any sort of surfing. The kind of big surging breakers.
That's for what were they used to call them, boogie boards.
Mm.
Yeah.
You always have the people that don't want to learn how to surf, they boogie board.
So boogie board conditions.
Yeah, I have gotten turned over pretty bad in a wave.
And you can't fight it, you just have to let it bring you back up. Because you get stuck down there, and if you fight, the harder it is to get out. That undertow can be so aggressive.
Yeah.
Yeah, no, it's scary. And so surfing, obviously, you can ride the wave and you have to somehow balance. And so kind of cool. Yeah, so people that surf, that's awesome. You can get up to 25 miles per hour, that's crazy. All right, so now let's look at kind of wave refraction. And so obviously, right, nothing's perfect, so your waves are never going to just approach your shore at a perfect 90-degree angle. So as our waves approach, they tend to bend, so our wave crests are nearly parallel to shore. And again, we mentioned wave speed is proportional to wave depth, so that's where we would invoke these shallow water wave conditions. And different segments of the wave crest travel at different speeds. So let's see. And so, right, this is just showing kind of our waves traveling. So, right, it's original deep speed in deep water, and then they start to feel the bottom and slow down in different surf zones. So, kind of have a curving. And so let's also look, so this is interesting because this also tells us maybe how things erode, or if you wanted to protect something, you could put a breaker. And so again, our wave energy is unevenly distributed on shore. So that makes sense, right? Because shore isn't just a solid flat piece of land for all these waves to crash up against. So there's features. And so we can see all these lines. So right, our crests, our waves are coming in. And so notice if you have like a bay, right? So it's like physically more surface area. So think about, right, if it was flat versus now the bay. And so that means these waves kind of get distributed. So you can see, right, they kind of fan out. And so this is going to be lower energy. And it even mentions how you might have deposition of sediment here in the bays from these waves bringing stuff in. And so notice, though, where the land juts out. So now if you have it jutting out, so the waves are kind of hitting it more, especially, you know, depending where your wave is coming. So it might erode like one side versus the other. And so you get a lot of, again, erosion right here at these jutting out points where they physically have, right, just more energy versus this where they're dispersed.
So it looks like on the sides of that point, it looks like the energy is being affected even though it's not yet hit. Like it almost looks like it's affecting the energy to the sides of it.
I'm not
Is that the case?
quite sure what you're pointing at, but like,
But if you look at the waves
are you looking at
going
this?
beyond that tip on the sides of it,
Right, so then it'd be dispersed again. Yeah, so it kind of gets dispersed because notice this is like another bay feature. So yeah, it does get more dispersed out.
but
So
even closer to the tip, like on the sides of that peninsula,
where here?
yeah, on the other side as well.
Yeah, so on the other side, right, we have another bay coming out, but then it's just this tip where it's kind of going around and getting, I would say, concentrated there, like kind of the energy. And this, right, more general, let's just say like more energy, right? So we have more erosion. That's like the really big picture, right? Is if your land is coming out in front, it's almost like meeting the waves. So there's more waves hitting it because there's more energy. You're also thinking surface area, right? It's like a small jut as opposed to, again, just a flat land. And so it gets concentrated around this tip, but then you're right, it goes back out again in these bays. So this is less energy, right? So now less energy here, and even less energy.
Maybe because it's further out, but between that less energy and higher energy, I was wondering if it's being affected.
Yeah, I mean, there'll still be, right, some effects, so it just is less pronounced, right? And you can see the waves kind of fan out as it hits. So again, right, it's probably being eroded here too, but then it'll like start decreasing. And so again, more energy released on our headlands, so we mentioned that, versus energy is more dissipated in a bay, and it's all just a gradient, right? So there's no clear drop-off points, just where it kind of looks like it juts. And then we would also consider, right, the motion of currents could also affect erosion. I think it mentioned specifically Rincon Point in California. And so maybe if the waves tend to always come in from like a current on one side, then you can have, right, a lot of erosion on one side. So it just kind of depends. Here's a picture that I was referring to. Right, so let's just say the waves tend to come in always from this side, so you would have, right, more erosion on this side of the jutting out peninsula versus here where you're right, they're kind of refracting around, and then there's less energy. So it depends, right, how the waves are hitting it. So this one, the waves are coming this way, so it's hitting this part more side on, versus, right, if the wave was coming from this side, that would cause different patterns, so kind of depends. Yeah. And so again, that's why we see erosion around what's called the headlands, and then our sediment in our bays. And so we also can bounce energy back. So kind of what I was saying, if you put out a barrier, a jetty, then your waves are coming in, but then they're going to be reflected back out. So that could create some dangerous conditions. And so it's showing this view here. So this is apparently Newport Harbor, again in California. And so they constructed this jetty that pops out to try to protect this entrance. But what that does is on this side then, right, where it's getting the waves hitting and then reflecting them back out because of our physical structure. So then this creates pretty choppy waters here. So it could be kind of dangerous, and I think it mentions that in the text how it's kind of dangerous conditions here. Some people take advantage and surf, but obviously, right, there's dangers in those choppy conditions. Let's see if we can make it to chapter 9. So standing waves, this is just when you have two waves with the same length moving in opposite directions. So this is kind of what you created with our little tub. And so this gives us, again, our kind of idealized wave here. And so this is where it actually defines the nodes and the antinodes, just like we defined earlier. Sorry, not very good at drawing sine waves, admittedly. So again, our nodes, which we said corresponded to our still water. And then again, note, right, our antinodes again. So just our crests and our troughs. And right, the water's just kind of sloshing back and forth like we saw in a standing wave, like we did in our little experiment. All right, so now let's look at tsunami. And of course, so what creates a tsunami wave?
Earthquakes.
Yeah, our plates. So our tectonic plates. So some sort of seismic activity, plates crashing together, and so that expands, right, energy outward. So of course, again, earthquakes are going to be the most common, and we'll probably give you the biggest ones. And you can also have underwater landslides, volcanoes, eruptions or a collapse, or even a meteorite. And so these have really long wavelengths. So then we could calculate our shallow water conditions. And so it says that it behaves as a shallow water wave since it is so large. And so it can encompass the entire water column, so it's kind of scary. And can even pass undetected under boats if you're in open ocean. And so speed is proportional to ocean depth. So again, very fast in the open ocean.
So the tsunamis can pass underneath boats before it reaches the shore, is that what that means?
Yeah, so it could be, right, like a deep water wave just kind of passing underneath. And then, right,
People might not know, so
Yeah.
sometimes there's no early warnings.
yeah, and they do try to put out buoys now. And so your book mentions that, so as we go, we'll talk about that. But yeah, so that can be difficult, right? How do you predict that? And so I know somebody else mentioned if you have a hurricane, right, you can detect, an earthquake. If you have an earthquake, you can detect those seismic waves, and that's going to be probably your first warning. And so right here we're seeing a triggering event. So of course, right, you have all our tectonic plates like we mentioned. They crash together, big movement, and that generates a huge wave, right? And here's, right, the little boat, like we were saying. So this incident could happen, and our boat's just sitting here happily, completely unaware of what's about to happen on the shore.
So are the boats in the ocean affected by the tsunamis, or is it just the shorelines that are affected by it?
It's usually just the shorelines from because basically what a tsunami is like a huge tide, right? And that's why they call it like tidal waves, but kind of erroneously, right? So it's just like a huge wave, right? And so that's all that's happening. So you have a big column of energy. So basically our wavelength, right, is so huge, because now we're looking, so that wavelength is 125 miles, right? So that's really large. And so it's taking up, right, our whole ocean. So like our whole ocean, just imagine, right, the whole ocean is jumping up and down in a big wave. But again, where the destruction comes from, and so this is maybe a better picture, right? So tsunami's coming in, but now our shallow water, so not only is the energy compressed, right, so we mentioned, so our height is also going to get amplified in the shore. And so that's kind of scary. But then, again, like I mentioned, you have your extreme low tide, because it's just a huge wave. So your tsunami creates that huge low tide, which could be your next warning. But then you have to have an equally high crest, right? So your trough has to match your crest. And so the devastation comes from, like, essentially a really high tide on land.
So does it pull the water from the shore to create it, or does the water come from the middle? Like,
Kind of neither, because like the water's just a wave, right? So just imagine, just think of like, you know, like the people waves for a second, you know, like the football fields. So like just imagine like a little wave, right? Is like you're just kind of jumping up and down almost. But then a big wave is going to be everything like coming up, like if everyone stood up in the stadium. But then think of that as your water level, right? So your water level is normally, you know, whatever height, and it jumps up and down as the waves come. But then if you have a large amount of energy, now it's going to jump really high, which is essentially the tsunami, right? So this is now good pictures, obviously terrible pictures because of what happened. But this is all that's really coming in, is like your whole ocean is coming up. So it's, it's mainly the water that was nearby that rushes in, but it's just like a really high tide. And so that's what happens in these photos. And so you may remember this, the 2004 big tsunami that hit that resort in Thailand.
Oh, there was a movie about that.
Yeah, I'm sure. I don't remember what the movie was called. I vaguely remember like celebrities were vacationing here and like were upset. I mean, that's probably why we heard about it on the mainstream. What was it? The Impossible. I'll put that on there. So yeah, I don't know how fictionalized that is, but that's where, again, Hollywood always has to take inspiration. But again, right, it's just like a huge wave. So you're imagining, just like we're going to see the tides at Crescent City, right? You have low tide, you have high tide. Well, what happened if you have a really extreme high tide and low tide? That's a tsunami, basically. And so right with the huge tide coming in, or your huge wave, it just brings in, a rush of water. And we mentioned.
If people are on like the shoreline, right, and the tsunami comes in, there's no way to survive like the impact of the water hitting you, right?
Probably not. I mean, right, at that point, it's just up to God or whatever you want to call it, right? Luck, providence, because not only do you have the sheer water, but it's also bringing in a bunch of debris and bringing down debris on top of you.
Also throwing you into debris.
Yeah, tossing you. So, yeah, surviving that would be. I mean, that's why it was super devastating, right? People lost partners, and I'm sure that's what happened in the movie too. Is you might have been trying to hunker down somewhere, and then the wave just took a person like from your arms, even. Like that's, you can't stop those forces, and.
I mean, people get pushed over when a little pool is cut, and
Yeah.
now just multiply it to several thousands of magnitudes.
Yeah.
Of what that much water compared to a little pool. I mean, you see YouTube videos all the time, somebody cut.
Yeah.
And it just sweeps them out.
Yeah.
Now imagine the ocean doing that.
Yeah, and I mean, you can see what it does. Like, it literally levels, like, villages and everything. So, and again, so why do most of these occur in the Pacific Ocean?
Well, we're on like all the major fault lines.
Yeah, and what is that called?
The tectonic plates. The ring of fire.
Yeah, I was looking for Ring of Fire. But yeah.
The largest body of free open water.
Yeah, that does help too, tectonic plates, but it is known, right, for that activity, so a bunch of tectonic plates, that's where you're getting all the earthquakes and volcanoes, so don't forget volcano eruptions. And so, yeah, like you're noting, so it's mainly damaging to those coastal areas, and again, it can just wipe out structures, obviously wipe out people. I think this picture is from Hawaii in 1946, so a lot of damage. Yeah, and a lot of this damage is, a lack of early warning. So I think after this, so now they have like a whole buoy system, especially in the Pacific. So the Pacific is more developed, and they try to, as best they can, detect tsunami waves coming. And so they also mentioned this Krakatoa event, which was pretty devastating back in 1883, where a volcano erupted. It also said it was like the loudest sound ever recorded. I'm not sure how they proved that, but that was kind of interesting. And then another, so Hawaii, this was the one that was there. So 7.3 on the new, I totally blanked on the new earthquake scale. So not the Richter scale, but the new one.
Wait, so they're claiming that in
Yeah, that's,
Do they have ways to do, like, measuring decibels back then?
I don't know, that's why I was fascinated by the claim. Yeah, it said the sound of the explosion was heard up to 4,800 kilometers away. So I think maybe that's why it holds the record, because of the distance, but I was also curious about
Well, because sound travel is different. You guys have like really high decibels that doesn't travel very much versus like that.
Yeah,
Right? Can't you have like it's something like a like bass versus like a high pitched thing?
yeah, like a bass will travel.
Much further than like a really high pitched.
Right.
Wow, that's an interesting claim.
Yeah, I thought it was interesting. I didn't dive deeper into how else
It's a
they.
YouTube wormhole.
So you can report back.
I'm just curious when people make giant claims like that.
Yeah, was it just somebody said, oh, I heard it?
Yeah, you know, and that's funny too, because if it's just based on that, people can think, you know, if they say, oh, is that what I heard?
Yeah.
Is that what I heard? Oh, I think I did hear that,
Yeah.
you know?
Let's see. So then, yeah, more earthquakes. So we can. There's our ring of fire, and also, so this is showing right significant tsunamis since 1990. So again, right.
They call it the ring of fire because there's like, volcanoes under the ocean in these places?
Or yeah, either on the ocean or on the surface. So yeah.
It's just overall more volcanoes.
Just really bad shit happens.
So yeah, lots of volcanoes, lots of earthquakes. Yeah, lots of tectonic activity, really bad stuff for summary. And let's see, so yeah, this was the 9.2 then, that was the famous one in Thailand. So this is, again, not the Richter scale, but the other scale, which I'm blanking, MW is the scale. I just can't remember the name.
This would be hard for me to adjust to, because I've always noticed the Richter scale.
I know.
Yeah, so how does that relate to it? Is that bigger or smaller?
Well, officially, this is, not to go on another tangent. So the problem is, so the Richter scale only measures waves in one direction. So I think we mentioned this previously. And this MW, the new scale, is supposed to be in like 3D and measuring like more of the overall wave picture. So what the claim is that there's no way to correlate the Richter to this new scale, which to me is bothersome. Like I want at least a rough.
Yeah, is it a lateral? Is
There,
it 9.2 a 5.4 on a Richter scale?
I have not been able to find something that nicely correlates that. If you could find that in your rabbit hole and share that, that would be awesome. Because I've always wondered that as well, and that's bothered me. But every explanation I've read is, oh, we can't correlate it because Richter's 1D versus this.
Well, that sounds like nonsense that they can't do that. Like,
I agree. I didn't want to go down the rabbit hole, but yeah. So.
Basically saying the Richter scale just isn't that accurate anymore, and so the new scale is way more accurate, so you can't like correlate it to the inaccurate.
Yeah.
somebody wanted a legacy.
My mind automatically wants to put it with the Richter scale, because correlate it, because then like San Francisco, is that or less, or, you know?
I agree with y'all. I don't have that data. I don't have that correlation. I don't know why it hasn't been done. But yeah, I was always taught that like a 9 would rip the earth apart, but not with this new scale. Like a 9 on the Richter scale. Anyways. Basically, large tsunami wiped out a lot. So, yeah.
It's 800,000 fatalities.
Yeah, so this is crazy.
Nuts.
And so part of that was the lack of a warning system in the Indian Ocean. So they now, I think, are working to build that. But again, just imagine, right, a huge wave, a really high tide comes here and wipes out your whole town, basically. So that's crazy. And then, so we mentioned, I think this was the Fukushima incident, yeah. And so this was kind of weird, the whole meltdown. I'm still not sure myself what happened. I think there's like a slight design flaw in this because they needed power to keep the nuclear waste cooled. So that was the issue, right? They had a bunch of nuclear waste. It was supposed to be circulating water. Usually, what you don't want something that's power dependent. That's why I've like kind of questioned some of the engineering that went in there. Because the idea is if you lose power with a nuclear plant, like it just shuts down. Like the whole thing's supposed to just shut down and be safe and not need power. Because this could happen. So disaster, right? So killed the power. And then that means the nuclear waste started heating up. So then it was released out. And I'm sure we're still tracking a few radioactive particles. And so we mentioned now we have what they call DART, so just our buoys, and try to give out watches and warnings for people. So you'd want to just evacuate the shorelines, obviously, and try to get ships from your harbors away. And then last little bit, I know we're over time, so you can take advantage of these waves and use them as energy. So, right, your oscillating wave can move a turbine. I just wanted to show this map because it's kind of fascinating. So it shows us where we have a lot of wave energy. And so anywhere in red might be good candidates for some sort of wave motion. So your book mentions like Spain, so that would probably be over here, why they're getting some energy. But right down at the tip of South America, Africa, and over at Australia here, so where they have those big winds, might be good areas, right, for these current generated power plants, but, you know, who knows? There's obviously questions of wildlife and all those impacts, and for us, though, right, not as favorable, pretty low waves energy, so probably not something the U.S. would pursue. All right, we'll end there. So we didn't get to chapter 9, so we'll have to kind of squeeze 9 and 10 in, hopefully, on Thursday. And then, yeah, you can grab your lab now. And then we can take 10 minutes so you can have your full 10 minutes. So we'll start 11:35 for lab.